All right, everyone. Thanks for attending this meeting over here. And first of all, we had a pretty big hiccup over here trying to get the server up and working and the display working. So this presentation is basically about porting network functions into KVM guest environment. And the approach that we took is essentially trying to, before calling anything real time, we first try to port most of the enhanced packet core network elements and try to essentially assess how fit KVM is for these applications. So from the previous presentations, I've kind of scaled back a little bit because, folks have talked about NFV, so I think everybody knows what NFV is and everybody knows what the advantages of NFV are. Also, as far as, why we want full virtualization, there's, lots of ways to virtualize the guest. There's also containers, but full virtualization is one area which kind of gives us a lot of advantages, the ability to run mixed OSs and mixed distros and, just basically own the whole stack and live migration and deliver a whole VM without any kind of strings attached as far as libraries or anything else. So I think everybody's very well aware of this. This is more of a throwback to a previous effort, which is carrier-grade Linux, so I'm not going to dwell too much on this. But the only thing I would say is that this kind of is similar to what we have today, where we had essentially a lot of gaps, and Linux was simply not fit to go into carrier-grade environment. And so what happened is that these gaps were identified. So you had, so what a gap is really, what it really is the expectation versus the implementation. And in some cases, there was no implementation. And I think in the case of NFV, we kind of have the same situation. So we have the situation of the things where the user has to be aware, just the way things operate. There's things where we have missing features. There's things where we need hardware extensions. And, there's also, of course, KVM and kernel enhancements and things of that nature. So eventually, the community got together. All these things got resolved. Now, when we're talking NFV, it's a much more complex situation because besides the fact that we're just dealing with Linux and KVM, we have a lot of different proprietary players, and these players are in many ways much more focused, and they could kind of just beam down to the problem and in many ways be able to deliver a better solution. So it's very important that we look at these gaps, and the gaps that we talk about in here is not just real time, but many other type of issues. And, having worked in the carrier-grade environment and, I've been out to, all sorts of different deployment sites and, supported customers and so forth, I got a, fairly good idea of what the carriers are really looking for when you deliver something to them. So this one I'll just kind of shortly summarize, so we know that the carrier-grade environment is extremely demanding. There's a lot of metrics. But the takeaway from this one is that, from this slide, is the fact that the ability to root cause problems and root cause them very quickly. So when you develop a network element, you pretty much are going to be stuck with the most basic tools to root cause a problem. So you're not going to have access to PMU and debug and things like that. And so before deployment, it's very, very important to use the tools that you would actually use out in the field and essentially use the same tools for development. Now, as far as the rest of the thing, as far as the stringent requirements like on data plane and, control plane and things like that, that's probably something that, that would probably take up too much time to go to this type of discussion. So just kind of a little bit of a dive into a wireless environment and how it looks. And so, pretty much no matter if you look at 2G or 4G, you pretty much come down to several factors. You have the control plane, you have the data plane, and you have the operations and maintenance. And when you look at the control plane, it's mostly events and timers. And, these things can range from extremes like land mobile radio networks where you have push-to-talk technology to just normal, PLMN, which is much more of a relaxed, type of latencies that we will be dealing with. So, when you take something like LTE, LTE has done a lot of things in the packet core because, we got rid of circuit switch, and there's a lot of what we call non-access stratum procedures that have been combined with access stratum procedures. But still, the bottom line is it's the radio interface that's really has improved over in 4G. That's really, that by far is giving us most of the capacity, that we're getting. So essentially, when we look at, let's say, in this slide, what we have yellow, which is trying to do a push to talk to green. So there's a lot of control messages going back and forth, and when you get down to it, each network element has a pre-allocated latency, and each link also has a pre-allocated latency. So from control plane point of view, what we're really dealing with is deterministic execution, but not just any deterministic execution, but latency under specific capacity. So each network element is kind of scoped to a certain capacity, and we have to be able to meet the latencies for various signaling that's flowing through the network. Okay, LTE. So this is like one slide, and it's kind of difficult to explain LTE in a single slide. But really, when you look at it, so it comes down to several things when you look at LTE. You first of all have the control plane and the data plane, and you could really look at the control plane, just like a normal switch where you're configuring routes, and then the data plane is pretty much like the switching portion of it. Of course, LTE is much more complex. It has the EU-tron portion, and it has the enhanced packet core portion. And most of the focus is really on the packet core right now because the packet core, for the most part, is just a standard server with Ethernet and storage. And so the radio part of it, and we'll see later on why it's so hard to virtualize the eNode B. So the radio part of it is kind of pushed off to the side right now, definitely for initial deployments. But eventually it's going to get there. There's this whole talk of a centralized RAN, and I'll talk a little bit about that, but not too much. I won't get into too much detail on that. So now we know when you kind of take a look at the EU-tron, so the eNode B is kind of responsible for the radio frequencies, for the radio technology, and also for allocating bandwidth, doing a lot of power management, quality management of mobiles that are roaming, and also standard EPS procedures such as attachment, detachment, and handover, and things like that. And the packet core has network elements. When you look at it, on the top you have the MME, which is the pretty much the brains of call processing, and then you have the home serving server, PCRF, which is the QoS part, and then you have the data pipelines, which is the serving gateway and the PDN gateway. And PDN gateway is really the thing that's in your phone, and so if you look at your phone, you'll notice that you have this APN thing, and that's the thing that you're really connecting to. So the whole point here is that a mobile attaches, and once a mobile attaches a bearer setup, that bearer is simply a GTPU tunnel. That GTPU tunnel is essentially used as a default gateway for a given UE, and essentially those packets just go through this tunnel, they're tunneled through that, and then they reappear at a PDN gateway, and then that PDN gateway then goes out to either, it could be IMS services, like a subserver, or it could just go out to internet. Another way to look at it is just a really big state machine. So, for example, if I have a mobile, and that mobile has just attached, and then that mobile happens to go inactive, and typically carriers set that to about 10 seconds or so. Then so that mobile will issue a release procedure. That release procedure will go up to the MME. The MME will tell the serving gateway, tear down the tunnel to the inode B, because there's no point of following that mobile as it's roaming through different tracking areas. And then eventually, there's something coming down for that mobile. It hits the serving gateway, or the mobile can instigate some data. The serving gateway tells the MME. The MME then basically does a paging request, and then what happens is that the UE does a service request, and then once it does that, then the bearers are set up, and then you have a pipeline that allows you to go out to the internet. Okay, on the radio side, it gets a little bit more complicated. So for a 20 megahertz carrier, for a 20 megahertz frequency, and I'm not going to go through the actual protocols, but just the amount of processing that the inode B has to do. So you have approximately 1,200 subcarriers, and so that's about 14K symbols per each subcarrier. And you divide this whole resource grid into what we call resource blocks. And these resource blocks is basically 12 subcarriers by 7 what we call symbols. And so now the capacity of a resource block can really range, because if it's control type of information, the resource block, the modulation can be maybe 2 bits per, it could be 2 bits per each resource element, or if it's QAM64, you could reach maximum bandwidth. So of course there's approximately 200,000 resource blocks if you're dealing with something like a 20 megahertz bandwidth LTE system. And of course, these resource blocks are not just allocated for data. I mean, they're allocated for all sorts of different resources, reasons, such as upstream, downlink, control channels, and they're allocated for system information base and, for the UE to be able to acquire bandwidth and so forth. But the bottom line is that when you look at the inode B, it has this real nasty scheduling algorithm. And so this scheduling algorithm has to be extremely smart. It has to be able to, for example, figure out fairness versus throughput. It has to do a lot of power control, fading, spreading, and things like that. And there's a lot of, there's a lot of engineering that goes into this thing, such as dimensioning and stuff like that. So when you look at the base processing of a inode B, I mean, what does it really have to do? First of all, it has to tunnel a lot of data plane. So a lot of resource blocks have to be allocated to data plane. So, when people say that it's 100 megabits per second bandwidth, well, that's only if you had one UE and you have no control traffic whatsoever. But in reality, you may get 2, 3, megabits per second. So the inode B has to do stuff like tunnel, a lot of GTPU tunnel. Well, actually, so GTPU tunnel data to the serving gateway and out to the PDN gateway. In addition, it has to do a lot of mobile control. So, that's a lot of QoS feedback that it gets from various mobiles. And then it also has to go through all sorts of procedures, network-like procedures such as attach, detach, and things of that nature. So later on, we'll kind of see what shapes the network. Why is it that we need this type of a ODP type of implementation to work with something like a inode B? So this is just a little bit closer look at the resource grid. So the only takeaway from this is that things happen very quickly on the inode B. So you have things that may happen every 500 microseconds, things that may happen every subframe, 1 millisecond, or every 10 milliseconds. But the bottom line is that the inode B is extremely busy scanning all these different resource blocks and reacting to them, whatever the request may be. So just an example of what call processing looks like, and this is just a simple, one service requests where mobile, for example, has to go from idle to active. And we're talking about 60 to 70 milliseconds before that mobile goes from idle to active. And so you have about 20 milliseconds for the UE to connect to the eNode B, and this is what we call the RRC connected state. And at that point, the UE is actually able to issue scheduling grants and is able to talk to the core. And then we have additional maybe 40, 50 milliseconds where we could actually be fully connected where the bears are established, and now we could talk end-to-end. So, you could just imagine you have, for example, 50 or 60,000 of these type of service requests, hitting the packet core. You could just see the overall messaging, the overall latencies involved, and then the overall timers, and just the number of timers that we have to support to be able to make that happen. So when you look at NFV, so I didn't put the eNode B in the virtualized column because the eNode B is a pretty challenging thing to really put into a virtualized column. But when you look at NFV decomposition, you kind of come up with control plane and you come up with data plane. And the control plane is typically something like ODP or DPDK. So you're dealing with a very tight loop. You pretty much want the scheduler out, the interrupts out, the timers out. And this is a lot of stuff that Rick and Jan essentially talked about yesterday. So you want firm isolation in the eNode B part. And then control processing, that's just a whole different, not a whole different thing, but it's quite different because there you could kind of deal with standard scheduling, standard Linux scheduling, so things like RR, FIFO, and things like that. But still, nevertheless, there's a lot of tuning that has to go on. You have to worry about all sorts of kernel threads that may be interfering with your latencies. A lot of tuning as far as the kernel is concerned, and so forth. So you kind of divide it up like this, and the eNode B part is kind of interesting because the eNode B part has to do way more than, for example, the serving gateway, because the serving gateway can practically become just an open flow switch configured from the control plane. But the eNode B just has to shuffle so much data to control processing, and at the same time, it also has to do so much radio management of the mobiles, and it also has to shuffle so much data. So the eNode B is slightly different. But this is kind of the decomposition. So I didn't put in the PDN gateway and all the other network elements. You also have IMS, and so most of the IMS signaling, if you go back to this slide over here, if you have a SIP server someplace within the IMS, most of that signaling actually just goes over normal data. So as far as LTE is concerned, it has no clue that it's actually, that you have a SIP session going through those channels. So what sort of, so I guess the takeaway, one of the takeaways, or actually quite a few takeaways, is that if we're running in a virtualized environment, we need deterministic execution. So, that was underlined yesterday in the initial presentation. We need to have a lot of coexistence between different type of execution loads. And so we're talking about things like data plane, control plane, which is, and so we have ODP, real-time, time sharing, and so forth. And it's still really not quite clear that all these things can really coexist within the same VM. It's very likely that we may have to decompose these and have some very, very high rate IPC between different VMs. And I think the previous talk kind of had a good lead into that, except I kind of didn't like the interrupt injection part of it. Then we have timers. So, anyone that's worked with, with networking, just knows that there's just, there's just thousands and thousands of timers, that are involved. So typically the way things work in control plane is that you get a request, you queue it up, you associate a timer with it, you send that off, something doesn't happen, the timer fires, then you retry again. And so a simple example is like, for example, a eNode B going off to MME and saying, okay, give me your PDCB context, right? It doesn't get the PDCB context, so the timer fires and it tries it again. So timers, we have to deal with that. Now the question is, how do you get a lot of timer interrupts into a GIST? So far, not a whole lot of luck. I mean, we can get a lot of timers into the GIST, but with a lot of overhead. Another one that I think a lot of people don't pay too much attention to, but carriers do, is CPU accounting. And with CPU accounting, as soon as you introduce VM exits, the carriers really don't care that you're running a VM and that VM is not supposed to know that it's not virtualized. I mean, they will want to know exactly, why is it that they're not getting enough time to run? So because they have very complex what we call load shedding algorithms. So when you go over a certain threshold, they will start denying requests. And so now, for example, if your vCPU is exiting, well, they might just try to spin up additional vCPUs, to compensate for that. But what's very important, well, actually, something that I go into later on, so there's no point, kind of belaboring this topic. And then we still have a few other gaps, that will be highlighted later. But the bottom line, the challenges are latency, performance at a certain capacity, with reasonable overhead. So we don't expect that, we could run, EPC, network element, with like, let's say 5% overhead. I think 15 to 20% overhead is something that's more in line. But then again, just the kind of flexibility that you gain is really worth it to go to NFV. So as always, Lmbench is always the preferable benchmark when you're dealing with wireless, because Lmbench allows us to measure the basic cost of operations. And given that wireless loads are typically so unpredictable, you can't just take any benchmark off the shelf and just run it. So Lmbench is our preferable way of doing things. And of course, RT test, cyclic test, and cyclic test to a certain extent is pretty okay. I think the previous presentation had a little bit better approach as far as being able to measure latency. And I think, in my opinion, we need to develop some kind of a latency test where we could test latency from the time something happens in the host to the time that something happens in the guest. But anyways, so what we have, we work with, and we try to make the most of it. And so some of the NFV attributes we test for is like commercial off-the-shelf hardware. Well, how suitable is it for VNF support? VNF decomposition, so we're pretty sure that there's no way that we'll be able to run everything within one VNF. And then improve operational efficiency, scalability. So we have issues with, so primarily scaling out, so live migration plays a big role there. Scalability, so when we're talking scalability, we're also talking a lot of memory, hot plug, and overcommit. So there are certain edge services that can be overcommitted. So the core network elements are not those, but some other ones can be overcommitted. So this is just, I don't know, this slide is kind of out of place, but this just kind of shows you how you do network element development. So you just kind of, have a call processing and you run some traffic and you kind of get a good fuzzy feeling that everything is kind of working fine. And then the real requirements come in. And when the real requirements come in, it's not just the call processing portion of it, but there's just all sorts of other things like auditing, lawful intercept, billing, and things like local maintenance terminal and tracing and stuff like that. And so that just goes to prove that you just have such a mixed set of processes and threads that are executing that really make wireless network infrastructure so unique to anything else. Okay, so on to the real problem. So on top is what we have today, and for the most part, we've been able to run with preempt. We haven't had to resort to preempt RT. Although when you look at the kernel, the current kernel has a lot of preempt RT in it, such as, interrupts running as threads and high-resolution timers, but, we're still not using mutexes and things like, priority inheritance and, things of that nature. But things are good, in this sense, things are working and, deadlines are met, both in the EPC and in the BTS. But now we're kind of winding up with the stuff on the bottom. And so it's kind of interesting because, I listened to the presentations yesterday and we seem to be coming to the same conclusions as far as, how to harden some of this execution. And so some benchmarks, that I ran, and this is a totally idle system, we basically, there's nothing running on this. And, so what we did is we basically moved the IO threads off of the vCPU threads, so there's no interaction between them. This is not a NUMA system, totally off the shelf, 12 CPUs. And I used the real-time option so we wouldn't be using too much paging. And so you run it on a host, and cyclic test looks perfect. You have 1 to 2% CPU overhead, which is really great. But then as soon as you move to the guest, you get some well, first of all, you get bad numbers, but the bigger one is the overhead that you get, and that's the real killer. Because with VNF decomposition, it is possible to kind of be able to decompose the VNF and kind of lower these numbers, or I should say improve these max numbers. But with this type of an overhead, there's really not much that you can do. And as you move towards FIFO and RR for the vCPU threads, you get better max times. And so that's a good sign because that means that we could probably move to preempt RT for host, and that'll even give us better numbers. And, one, I guess, point is that when we're talking about max, it's not necessarily too bad if your max is out there. It's just a question of it's an outlier or if it's something that's like within 2 or 3 or 4 or 5% of time of occurrences when you get scheduled. And so that's probably something that we should add to cyclic tests where we could kind of see, okay, well, less than 0.5% got this max time, but then most of it, we never actually hit that max time because this could be kind of misleading. The conclusion here is the way things are right now, it basically kills COTS because, we would have to, get some big server that is like 64-way NUMA, and, that's not something, that's not a direction we want to move into. Setting vCPUs to RR5 does help limit the max. Future direction is host running in preempt-RT. So either isolate CPUs or no hertz full. So this would be primarily for data plane applications, and offload the RCU processing. So, just standard practicing that was talked about yesterday. As far as moving preempt-RT into the guest, probably unlikely because the problem is that preempt-RT does have its own costs. When you're dealing with mutexes and priority inheritance and transitive, priority inheritance and those type of things, does have its own costs. But you never know, we might wind up there. And for control plane, just standard, standard Linux with your FIFOs and RRs and things of that nature. The issue, again, is driving enough timer interrupts so we could actually process events on time. And again, we're down to this control plane, data plane decomposition. That's kind of something we do not want to do, but if we need to, then something we will do. Timers. So Lmbench, you run the timer benchmark, and what happens here, there's actually 2 hits you take. So the benchmark, first of all, has very high overhead if you're running it in a guest. And secondly, again, your CPU is 20% higher. Well, that's no wonder because that's kind of similar to what cyclic test is doing. But I think for that one, we have a pretty good workaround. And actually, it's the solution that I've seen with most of the network elements that I work with. There's typically a dedicated timer task. And so you essentially coalesce timers. So if somebody asks you, okay, I want to do a timer at 500 microseconds, well, you coalesce the timer to like 2 milliseconds. And actually, if you look at driver timers, timer drivers, they tend to do the same thing. They tend, they tend to coalesce as well. And so when we do that, the CPU pretty much drops to negligible. And but then, of course, the big question is when we load up a full system and we have let's say we have an MME pool that is covering like 6 million subscribers, and we get 20,000 service requests, that's 250 microseconds per each service request. Can we actually scale this way? That would be the big question. So this is still a TBD, but this, I think, appears to be realistic to be able to do this within a guest. And then comes the real troubled one, and this is the real scary one because you run latency memory read, and what happens is that your CPU goes to 100%, and this benchmark tends to just kind of hop around and randomly read different strides of memory. And so it's, first of all, trying to go outside of the TLB and also trying to go outside of the cache. And so this is not good. This is really, of all the drawbacks, of all the issues that I've pointed out here, this is probably the biggest one. When you run bandwidth memory, everything looks great. This is like very realistic, no problems here. Latency mmap, latency context. So mmap is off, but we could live with mmaps. How often do you do forks and execs and things like that? That we can handle. But, we cannot handle the context switches. If you introduce 8 megabytes of noise, you're dealing with about 81% overhead, 81% extra CPU usage. And so this benchmark, all it's doing is just context switching. So we're not talking context switching of the overall application, but that's what the benchmark is testing. So, I looked at this very closely, went through, profiling and so forth. And the only thing I could point to is the nested walk. So, we're doing 24 memory lookups instead of 4 memory lookups. That's about the only thing that I could point to. And to mitigate the thing is basically spread your memory across 4 different CPUs, and now everybody kind of has their own, has their own cache and has their own intermediate page table walk cache. But the conclusion here is really the nested page table walk, and the question is, when you look at the actual processors out there, the question is, where is this intermediate page table walk cache, and how can you tune it? How can you even access it? And, when you get it, we work with some vendors, you ask them, they don't know where it's at. They don't know, what its size is. And, from ARM point of view, ARM has some very finely flushing where it's able to flush the leaf entries. Currently that's not in the kernel. But at least it leaves the GFN to PFN mappings intact for page table walks. So this one really needs a lot of more work, but I think the big thing here is to talk to the hardware vendors. And I think that's where a lot of differentiation comes into play if you're talking to hardware vendors. Let's see. Okay, so that one is done. CPU accounting. So CPU accounting, so first of all, it has to be cycle-based accounting. So if you go into wireless environment and you're dealing with tick-based accounting, that's completely out of the question. Secondly, preferably per CPU, and in this case we will be dealing per vCPU. Now carriers like to manage themselves, and if there's anything wrong, they want to be able to root cause and analyze the problem immediately. So, before we had like all sorts of different modes, execution modes, and they wanted to know, okay, well, why this mode is longer or shorter. Well, now we have exits. So all of a sudden, we do an exit and we're stuck in some mode for like who knows how many milliseconds. Well, the carrier really doesn't care that you're running within the VM. As far as the carrier is concerned, this is a real network element. And the carrier, so we tend to be very religious about the fact that you don't want to expose that you're a VM, but to the carrier has to know that, okay, I'm exiting. And the reason that I'm not getting enough CPU to run is because I'm exiting. And so then the carrier is, can apply certain load shedding type of algorithms. And more importantly, as far as the MIB, like the SNMP MIB, I mean, most of the stuff within the infrastructure is done through SNMP, TREBs, that can be augmented with exit statistics as well. And the reason I mentioned that is because, I worked at Bell Labs where we did, live kernel patching, and worked with push-to-talk technology at Motorola. And that's always been the biggest issue. And the problem is that when you go out into the field, you can't use PMU type of tools, you can't use GDBs, you can't use any of that stuff. The only thing that you could really use is pretty much native accounting, and that's about the only stuff that, I mean, if you're lucky just to get some tech to go out there and just do some PS commands for you, or run some command, that's about as much as you get out of it. Or you go climb Sears Tower, like in my case, I've been in some very odd situation where I had to go and retrieve logs from some odd places and things like that. So, this I think is not a critical path to releasing to make NFV happen, but it's something that will definitely come up. At least in my mind, I'm pretty sure that will happen. Next one is decomposition, VNF decomposition. So a lot of folks, there's this whole thing called VNF, what we call function graphing, and essentially, if you want to scale, there's two ways to scale. You could scale vertically and you could scale horizontally. And essentially, horizontal scaling is a much more difficult thing to do, just simply because you have to take network elements and you have to make sure that they are able to sustain that kind of capacity. So vertical scaling, where you throw a lot of VNFs onto single box, is pretty much the way that things are going. So here what we see is big requirements for very robust inter-GIST communication, share memory, which is really discoverable on demand. So not something like just plugging in an IV share mem, but for a VNF to be able just to probe and discover a share memory segment, map to it directly. And of course, we also need very fast signaling. So something like IV share mem type of signaling, where you have event FD, tied to an IRQ FD and things like that. That's kind of most likely won't cut it because typically natively, you're using POSIX type of calls and things like that. So one way is to maybe leverage off of some of the power management instructions. It's just that some of these instructions are not too intelligent. On ARM, for example, if you do a set event, that just kind of tends to wake up everybody. But if you had extensions where you could associate each one of these with the GIST, and then the GIST can be in a sleep, and then you could just issue a set event with the immediate, well, that I think is something that is more likely to scale. VM management operations. So a lot of work has been done on that on ARM. So what we've done is what we do basically when we migrate, we essentially break up huge pages into small pages. And so that allows us to migrate very quickly. from one machine to another. And then as soon as we get to the destination, we coalesce and we get the performance. Of course, there's more work to be done in this case. Looking at x86, there's a lot of reverse mapping, a lot of optimization that's been done there. But, we've seen migration times which are like, literally like 100x as far as migrating from one host to another. Another big issue is like memory overcommit. So we have an issue with ballooning. So right now, if you inflate, there's a race condition. So your inflate is, for example, asking for X amount of memory. But by the time it gets to the VM, from QEMU to the VM, that VM may have grabbed a lot of memory, and that essentially leads to a complete lockup. And there's a lot of services that we want to be able to overcommit on. And so this is something that, we worked on a patch. The patch is not complete. It's certainly better what's out there right now, but it's something that we have to do more work on and make that happen. And then some odd ones, which I can't explain from Lmbench. So system calls. So I have no idea, or signal delivery. In my mind, there should be no difference between native and GIST. I don't know why is it that GIST is longer than native. Things like latency for fork exec shell, that's understandable. There's a lot of IPIs that go back and forth. So IPIs, unfortunately, are still, unlike posted or VTD posted interrupts or, JIC-V4 interrupt injection. There's not much we could do here. And typically in carrier grade, we don't like to deal with threads because threads are troublesome. We usually like to save FDs, checkpoint the state, and then restart the process. And if you have threads involved, it gets more cumbersome. But it's something that may change. I think the big deal here is like pulling off-the-shelf software, essentially, that is just expecting to do a lot of forks and execs, and then all of a sudden you run into something, this kind of a situation. And this kind of would finish up the presentation. When you look at the overall gaps, and I'm not going to go through each one of them, but you have gaps which are related to awareness. You have gaps related to hardware. You have gaps related to enhancements. And this is really not an issue that can be addressed by any one person or maybe even any one company. I think, similar to like carrier grade, where there was a lot of synergy, a lot of people working together. It really takes a lot of people, low level. I think people that really show up to these conferences to be aware of like, okay, well, what are we doing in NFV? And it's these people that can actually close these gaps. And it also requires very close working with the hardware vendors and, to close some of these gaps. Some of the interaction I've had with, I'm not gonna name the vendor, but like, for example, they can't do crypto because the deal is that like, if it's behind the IOMMU, and, they basically offload a IPA address, there's, device pass through. VFIO is broken. It's not going to work. And a lot of devices, for example, get passed through, but they have no, IPIs associated with them or no SMMU associated with them. So VFIO just like just gives up because, it doesn't know what kind of device it is. So that's pretty much it. I don't know if there's any questions.